Hi, my name is Hua Liu, and I'm very excited today to present our research work, language-driven semantic change detection in urban maps via multimodal deep learning. This work was done by me and Zihao. We are both senior and a graduate student working in the Map Lab with Dr. Mahanti at Harvard College. All right, I'll just jump in. So currently, accurate and up-to-date maps are very fundamental to the safe and efficient operation of autonomous navigation systems, particularly in a dynamic urban environment. Systems like autonomous vehicles, robots, or any other intelligent system, they all rely on these maps for robust trajectory planning, effective obstacle avoidance, and accurate localization. And the sources of this map data uncertainty in urban driving environments can arise from multiple factors. For example, the building footprints uncertainty, intersection topology uncertainty, or temporal map changes, such as construction, among other sources. However, the research in map uncertainty quantification has largely focused on static assessments rather than dynamic and real-time estimation. For example, heuristic or statistical method using Gaussian mixture model or Gaussian processes to quantify uncertainty in LiDAR-based maps. However, these methods are not generalizable and cannot dynamically track uncertainty evolution over time. Also, for the SLAP methods in the existing literature, they can improve localization, but they typically do not track semantic consistency across different time frames, which limits their effectiveness for long-term map uncertainty monitoring or explicit change detection. Furthermore, the approaches like predict occupancy maps using deep generative networks, they can infer missing regions probabilistically, but often lack structured uncertainty tracking, which restrict their ability to provide interpretable explanations for detected inconsistencies. Finally, we also have some methods that is online HD map estimation. They can refine maps dynamically, but their primary focus is on trajectory prediction rather than assessing the uncertainty of the underlying map as representations. And also, more recent approaches use deep learning for detecting semantic changes in aerial imagery or street level views. However, these methods often require extensive label datasets for training and may struggle with novel or unseen changes. So, in summary, the existing approaches to map uncertainty quantification and change detection are often heuristic based, using a single sensor modality designed for static environments, make straight noise assumption on the uncertainties of the map itself, and also lack the real-time semantic aware capabilities required for complex urban settings. To address the first gap, we always asking, is there a way we could use learning methods in each sensor modalities, be it camera or LiDAR, and then perform sensor fusion? To address the second gap, we always asking, is there a way we could characterize the map uncertainty without strict assumptions on the noise distributions? And now the existing literature has already shown that indeed we can do both of these things, but there is limited literature on the last point, which is to look at the foundation models more generally, or specifically look at the vision and language models to understand the semantic reasoning in addition to geometric reasoning. And there is rich literature for this in the robotics community that we can look for inspiration. So now I want to spend some time explaining the vision models in general. So the traditional vision models are excellent at detecting objects, but they lack contextual understanding. So just think of a convolutional neural network, for instance. On the other hand, language models like ChatGPT 3 in 2022, they can understand context and relationships, but cannot see the physical world. For instance, a language model can explain what is a traffic light, but it cannot tell whether the light is currently red or green without the visual inputs, right? However, the large multimodal models, like the ones shown at the bottom, CLIP, which is the contrastive language image pre-training, SAM, segment anything model, and Dino V2, they can bridge this gap. More generally, these models are referred to as foundation models because we can use these as backbones architecture to build any model for a domain-specific task. And surprisingly, these models can also perform zero-shot learning, which means they can recognize and understand objects they've never been specifically trained on, and this capability is critical for autonomous systems that encounter novel scenarios in dynamic real-world settings, which is critical for safe and robust navigation. So our key contribution based on the insights into vision models is, first of all, we propose a LiDAR camera sensor fusion framework for quantifying dynamic map uncertainty, as well as comprehensive scene change understanding. And also, we use novel large vision language model to perform zero-shot semantic segmentation for more robust change detection. Finally, we also propose online KL divergence-based consistency tracking algorithm and evaluate its efficacy under adverse weather conditions. And then I'll structure the rest of my talk in 3 parts. First of all, I'll walk through our proposed framework, including the vision module, LiDAR module, and consistent monitoring and sensor fusion. And then I'll discuss our experimental setup using the Virtual Kitty dataset. And finally, I'll present our key results showing both individual sensor performance and benefits of sensor fusion when tested on adverse weather conditions. All right, so our framework detects map anomalies in urban drive scenes by jointly analyzing camera imagery and studio LiDAR point clouds derived from depth maps. On the vision side, we use vision language model to identify map discrepancies and then perform a pairwise comparison of before and after masks to generate a per frame change distribution whose KL divergence measures the severity of the visual disruptions. On the geometric side, depth images are back projected into 3D, range filtered, and normal augmented, and then fed to a learning point cloud segmentation network. Finally, a sensor fusion layer combines the vision and LiDAR divergence scores through a weighted sum, which produces a single scalar that flags map changes and encodes confidence. And the heuristic weights balance modality trust under clear versus degraded conditions. And in our framework, what sets our approach apart is the principal integration of semantic change detection from both vision and LiDAR modalities, using the normalized KL divergence as a unified metric. Unlike the traditional voxel level or object counting methods that are sensitive to sampling density, occlusion, or spatial alignment, our framework interprets maps changes as a shift in probabilistic semantic distributions, which provides a modality agnostic and resolution invariant signal. So let me right now dive deeper into the vision module. We start with zero-shot object detection using state-of-the-art models. In particular, we use grounding Dino V2 to localize critical infrastructure, including traffic light, traffic signs, guardrails, poles, and any other attributes using text prompt without retraining. And then the segment anything model provides initial object masks, and we then use prompts, including traffic light, traffic signs, and anything I just mentioned, to refine these masks. This is where the language component becomes crucial. And finally, we perform a semantic change detection using KL divergence to measure the differences. And the visual examples here shows how we can detect the traffic signs have been removed between the before and after images. Our LiDAR module uses PointNet as a main architecture backbone. We chose PointNet because it's lightweighted and efficient, which is super important for real-time applications. So the whole process starts with the depth image and semantic label as input. We pre-process this data to create segmented point clouds using PointNet, And then we apply the same KL divergence approach to detect the geometric changes. And this gives us the precise 3D understanding of what has changed in the environment. And now, applying the point cloud or any learned method to get these semantic discrepancy scores is not trivial. So here, I'll talk about our key pre-processing steps. So we convert the 2D depth images into the 3D point clouds using the camera intrinsic, and then we apply range filtering to remove simulator boundary artifacts that could confuse the system. After this, we compute the local service normals using the KD tree search, which helps captures important geometric structure. And finally, we assign the semantic categories using the ground truth annotation with the unified class labels. And the whole pre-processing process ensures us that we'll get a LiDAR module has rich and clean data to work with. So in the consistency monitoring and sensor fusion, we compute a KL divergence from both vision and LiDAR module. Vision module will provides semantic richness, and LiDAR provides the geometric reliability. And in this case, we perform a loose weighted fusion where the weights are adapted based on environmental conditions. For example, in rainy weather, we weight LiDAR more heavily since the vision is degraded. And the whole adaptive fusion is key to our system robustness. And in our case, this is a loose sensor fusion, right? Which means the coefficient can be adaptively tuned or even learned using backpropagation. In the future, we'll try some tighter fusion of the weights. And now I'll talk about our experimental setup, metrics, and baselines. In our work, we use virtual kitty datasets. We chose this dataset because it provides pixel-level ground truth, which is critical for evaluating semantic change detection. And like the real-world datasets, it also allows us to stress test our approach under control conditions, such as rain, fog, or different lightings. Another advantage is that it includes a variety of target objects like buildings, traffic lights, traffic signs across multiple sequences that enable fair and comprehensive evaluation. To simulate the real-world map changes, we programmatically remove objects from the scenes. For example, we delete a traffic sign or a light pole or even the entire buildings while keep the rest of the environment consistent. This way, we precisely measure how well our method detects these changes. And here we compare our method against several strong baselines. The first is CLIP, which is contrastive language image pre-training, where we use patch differences between before and after images to detect changes. The second is Lofter, a detector-free local feature transformer that matches key points between frames. For LiDAR, we use the J-card distance, which measures voxel overlap, and then we combine the modalities through a fusion step using a weighted sum of vision and LiDAR scores. To evaluate the performance, we rely on two metrics. KL divergence measures how close the predicted anomaly distribution is to the ground truth, where the lower is better, and then Pearson correlation, they capture spatial agreement between the predicted and actual change maps, and the higher is better. Together, these metrics let us quantify both accuracy and consistency across the method. And we proposed 3 evaluation questions based on our experiments. First is, how well do the predicted anomaly distributions align with the ground truth changes, which is induced by simulated infrastructure removal? And then, how accurately can each individual modality detect semantic changes in the map under normal and degraded conditions? We're also curious about, can the fusing information from vision and LiDAR improve map change detection in diverse conditions? And I'll now just present our key results. Note that for the sake of time, I won't be able to present all the results, but they're all in the paper. So these results shows our vision module working on real examples. The first column shows the before images, and the second column shows after images, and the third column shows our DynoV2 based patch pattern contrast. Warmer colors indicate higher change probability. And the fourth column shows the semantic differences we detected. And you can notice how our system correctly identified where traffic signs, guardrails, or any other infrastructure have been removed. This demonstrates our vision language approach can capture meaningful semantic changes. And here are the quantitative results for our vision module. As shown in the table, when tested under normal weather conditions, our method achieves 95% overall true positive rate, which is significantly better than the baseline. Clip achieves 75% and laughter achieves only 63.8%. Whereas we perform well across all categories, including buildings, traffic light, and traffic signs. And this demonstrates that by combining zero-shot learning with proper semantic understanding, we can indeed do improved map change detection. Also, our LiDAR module also shows strong performance. The top graph shows KL divergence value over time for two different sequences, and the bottom graph shows ground truth changes over the same time period. Notice how the KL divergence peak align well with the period of actual map changes. This shows us our LiDAR module can reliably detect geometric changes in the environments. So under adverse weather conditions, our sensor fusion module approach still maintains a very strong performance. As you can see, our KL divergence is 0.13 compared to 0.89 for clip and 0.35 for laughter. And our Pearson correlation is 0.69 compared to 0.37 and 0.26 for the baselines. And at the same time, under the adverse weather condition, our method's KL divergence shows 0.13 and Pearson correlation shows 0.68, which is not degraded too much. So to conclude our work, we show that our proposed sensor fusion framework with KL divergence-based scoring achieves high performance to identify map changes under normal conditions and maintains it in adverse weather. We also shows that how real-time anomaly detection with spatial heat maps can provide autonomous systems with change alerts and accurate localization, as well as address the critical gap between static maps and dynamic urban environments for safer navigation. And finally, a core contribution of our work is to show how integrating large vision language models can enable detection of novel infrastructure changes without training. And that's it. I want to say thank you for listening, and I want to say thanks to Prof. Mohanty and all the other collaborators in our lab, which gives me advice and suggestions for the whole project. Thank you.